The Quantum Node, Building Bridges to Innovation in a Quantum Age. Written by William Houston. Read by William Houston. Introduction. A Star to Light the Way. A Love Letter to Human Communication. Technology is at the forefront of every industry, from finance to manufacturing, and from the arts to sports. We are in a world where if you are even remotely in the know, you can name at least one celebrity engineer or scientist. The scientists and engineers pushing the boundaries of what is possible are now receiving the recognition that was once reserved for pop stars. Engineers turned CEOs like Robert F. Smith, chemical engineer at Kraft General Foods, now CEO of Vista Equity Partners, and Mark Cuban, founder of AudioNet and now CEO of Cost Plus Drugs, have become role models for what young technologists aspire to be. What I've noticed about the celebrity engineer craze is that there are many different fields these engineers hail from. But one field I don't often see represented is telecommunications. Most modern technology is propped up by services implemented and designed by network engineers. Yet, you don't see Comcast or AT&T churning out celebrity engineers. You don't hear about telecom startups causing a global sensation. Why might that be? The internet. Anyone in the field of network engineering understands that the internet is a massive network, the largest network, composed of all the smaller networks on the planet. This is something we inherently know, and anyone who implements or troubleshoots WANs secretly, or maybe not so secretly, takes pride in playing a part in it. Across the 7 layers of the OSI model, or the 4 layers of the TCP/IP model, everything that happens over the bits, packets, and frames of the network is implemented or troubleshot and monitored by a network engineer. This gives a tremendous amount of influence to backbone, carrier, and enterprise level engineers in how humanity communicates. I believe the ease of communication in the 21st century is woefully taken for granted. If you disagree, try handwriting a letter, putting it in the mailbox, and waiting for it to arrive. Then tell me if you prefer that to a text message. The power of a telecommunications engineer. Because of this, I think telecommunications engineers hold significant power, not just in their technical roles, but also in shaping the ethical philosophy of this field. In the little over 20 years since Y2K, if you're old enough to remember that, it might be time for your quarterly doctor visit. We've seen technical advancements that previously took centuries to achieve. The internet is the catalyst that has accelerated these changes. It has enabled global collaboration, near instantaneous access to humanity's collective knowledge, and tools to program and build in the cloud. These advancements have fueled every subsequent technological revolution, from genome mapping to communication with geosynchronous satellites, and everything in between. I believe we've given up too quickly on the cool things and rockstar engineers that the internet, the backbone of innovation, can produce. This book's overall message will highlight those things and get some of the world's network engineers to think about the amazing things they can do outside of maintenance windows and OAM. Celebrity telecommunications engineers. I believe it's past time for network engineers to be recognized alongside their mechanical and software engineering peers. This recognition starts with being more vocal and innovative in communicating changes within the field. Gone are the days of star telecom scientists from Bell Labs like Shirley Ann Jackson, who took her background in theoretical physics and applied it to fiber optic cable technology. So, who has taken her place? Who is the Mustafa Suleiman telecommunications? Or has the industry aged to the point where innovation is stalled? Is telecommunications simply the infrastructure running quietly in the background, like an older person trying too hard to fit in, past its stage of being cool technology? I don't believe this is true. In 2020, I watched an experiment conducted on the ISS, the International Space Station, where an astronaut tested the viability of manufacturing fiber optic cable in space. The rationale was simple. Space offers an ultra clean environment, 250 kilometers above Earth's dusty surface. I'll delve into the details of this later in the book. This experiment could represent the first step in establishing a practical and feasible space manufacturing industry, and that is exciting. We are now 5 years away from the bicentennial of telecommunications, from the invention of electrical signals via the telegraph to electrical signals over copper and switch networks to IP addressing, photon transmission through glass, and satellite internet beamed to any location on Earth. telecommunications has continually evolved. These innovations have enabled seamless communication between humans, not only on Earth, but also in space. As we approach a paradigm shift in human interconnectedness, and even a potential untethering from our own home planet, the question remains, how will telecommunications evolve? And who will be the superstars leading this transformation? Part 1: Science to Systems, the spark of curiosity behind tomorrow's technologies. Science. Noun: the systematic study of the structure and behavior of the physical and natural world through observation, experimentation, and the testing of theories against the evidence obtained. Archaic: knowledge of any kind. From a young age, I've been deeply curious about science. And when I say science, I mean it in its most fundamental definition. I've always loved to explore, discover, and ask why. I didn't always know the scientific method by name, but the instinct to question and search for answers has always been there. Back then, I didn't yet understand what technology was or how science could be applied to create it, but the curiosity was undeniable. Where I'm from, there weren't many outlets to nurture scientific curiosity. So, like many others, I took other routes through life. But eventually, I found my way back to what first fascinated me: the drive to understand how things work and how that knowledge can be used for the benefit of all. That journey led me into the world of telecommunications, specifically to the intersection of applied physics and fiber optic communication. What pulled me in was the realization that this entire industry is built on a foundation of scientific discovery. Many people in tech, especially in networking, often only know their specific task or the tools they work with. It's easy to get lost in the day to day operations, moving from ticket to ticket or maintenance to maintenance. But at its core, telecommunications is the result of nearly 2 centuries of human curiosity and collaboration. We are not just techs and engineers, we are the caretakers and builders of one of humanity's grandest scientific experiments: how to connect across greater and greater distances. It began with the telegraph, a short range electrical transmission system born out of the inefficiencies of writing and sending a letter. Using electricity, the fastest force we knew of at the time, to send simple messages was revolutionary. That innovation evolved into telephone conversations and eventually into global voice and video communication. But we didn't stop there. Scientists and engineers continued pushing boundaries. They discovered that light could travel faster than electrical signals and found a way to harness it through fiber optic cables. This gave rise to erbium doped fiber amplifiers, EDFAs, which allow light signals to travel longer distances without degradation. That's applied science at its finest, turning theory into tools that transform the world. Today, we're moving terabits of information in a second. Smaller data packets travel in milliseconds. These innovations no longer only support voice. Thanks to pioneers like Marion Croak and Shirley Ann Jackson, we can now have face to face meetings with people across the globe with crystal clarity. And we're not stopping at Earth. Communication is already extending into low Earth orbit, LEO, via satellites, and the future will likely include real time exchanges between the Earth and the Moon, or even Mars. The same spark of curiosity that created the telegraph is now pushing us into interplanetary communication. Much of this is driven by applied science. Particle physics, for instance, has given rise to quantum and neutrino based communication, technologies that might one day become foundational. Applied science takes abstract theory and grounds it in the real world through technology. It's what bridges the gap between the lab and the street, between the experiment and the everyday. We can grow on this too. I read scientific books like Fear of a Black Universe by Stephen Alexander, Quantum Supremacy by Michio Kaku, and The Elegant Universe by Brian Greene, and I feel a fellowship. Though these are famous physicists from Harvard, Brown, and Oxford, respectively, as an engineer, I understand my field well enough to understand how they apply their knowledge to affect what I do. So here's a real quick question: what can you apply? What science fascinates you? And how can you transfer that knowledge into something that helps the world? Let this be a call to the next generation. You don't have to wait to be a scientist in a lab coat. Your curiosity is enough. Start with your questions, stay rooted in the fundamentals, and then aim higher. The future of communication and many other industries will be shaped by those bold enough to ask why and brave enough to build the answer. Chapter 1. Keep that same energy. How telecommunications is pioneering sustainable energy. In the era of rapid digitalization, telecommunications has emerged not only as the backbone of global connectivity, but also as a leader in sustainable energy innovation. From leveraging cutting edge heat displacement technologies to embracing renewable energy sources, the industry is redefining how we power the modern world while mitigating its environmental impact. The massive energy usage of data centers. Data centers, the lifeblood of modern telecommunications. Digital infrastructure and the future of AI are among the largest energy consumers worldwide. According to recent studies, data centers drive about 1% of the global electricity demand, a figure that is only expected to grow as our reliance on cloud computing, artificial intelligence, and Internet of Things (IoT) devices expands. Traditional data centers often rely on energy intensive air cooling systems to maintain optimal hardware performance, with significant portions of their energy usage dedicated to cooling rather than computation. In the US alone, data centers consume an estimated 70 billion kilowatt hours of electricity annually, producing substantial carbon emissions. The industry's growing demand for power presents a unique challenge: how to meet the energy needs of an increasingly connected world without exacerbating climate change. This has challenged telecommunications and tech companies to explore innovative solutions that reduce energy consumption while maintaining operational efficiency. Revolutionizing energy usage with heat displacement and liquid. One of the most exciting developments in telecommunications is the use of liquid based heat displacement systems. This technology involves immersing servers and other data center hardware in non conductive liquid to efficiently manage heat. An example is the central computer on the ship Icarus in the 2007 movie Sunshine. Look it up, it's worth a watch. Traditional air cooling systems are energy intensive and require vast amounts of electricity to maintain optimal temperatures. Liquid cooling, on the other hand, dramatically reduces the energy footprint of data centers. This technology is not just about efficiency, it's a paradigm shift in how we use energy. By displacing heat more effectively, data centers can operate at higher densities and still consume less power. Moreover, the displaced heat can be redirected and reused for other purposes, such as heating nearby buildings or powering industrial processes. This circular approach to energy transforms waste into a resource, setting a new standard for sustainability. Solar energy, clean and abundant. By now, solar energy is commonplace, but there are still ways to improve on this technology, and telecommunications companies are increasingly turning to solar power to fuel their operations. Solar farms are integrated into data center infrastructure to harness the sun's energy and offset carbon emissions. Solar energy is particularly advantageous for remote telecommunications installations where grid power is unreliable or unavailable. By investing in solar, companies reduce their dependence on fossil fuels and take a proactive stance in combating climate change. The scalability and decreasing cost of solar technology make it an accessible and impactful solution for powering a sustainable telecommunications network. Nuclear energy, overcoming misconceptions. While nuclear energy has long been stigmatized due to safety concerns and cultural connotations, it is gaining renewed attention as a reliable 24/7 energy source. For data centers with constant power demands, nuclear energy offers unparalleled efficiency and stability. Modern nuclear technologies are significantly safer than their predecessors, and the ability to generate massive amounts of power with minimal land use makes nuclear a compelling option for energy intensive telecommunications operations. By advocating for nuclear energy, the telecommunications industry has the potential to reshape public perception and highlight its role in a sustainable energy future. With the advent of AI or LLM organizations, the need for power in data centers has grown exponentially. Companies like Meta, Tesla, and OpenAI have gone all in on public private partnerships to develop nuclear energy plants. There will be a long road to making nuclear something that the wider society deems safe. It will be a long road before counties and municipalities want reactors in their backyards. But if done right, this can truly make a change to the energy status quo. Biodegraders, transforming waste into power. This is a less known and admittedly less appealing option in the fight against climate change and the ability to cleanly and sustainably power the future of communications and technology in general. Telecommunications companies are also exploring biodegrader technology to convert organic waste into usable energy. These systems break down food scraps, agricultural waste, and other organic materials, producing biogas that can be used to generate electricity. Biodegraders not only address the growing issue of landfill overflow, but also provide a renewable energy source that reduces dependency on traditional fuels. By implementing biodegrader systems at data centers or telecommunications hubs, companies can create a closed loop energy system that turns waste into a valuable asset. This, like nuclear energy, comes with stigmas and reticence to having these located in populated city centers. The biodegrading process uses waste, which comes with smells and possibly lower surrounding property value. No one wants this in their neighborhood. If energy can be transmitted from a longer distance with this process, it can be a great source of sustainable energy, but it will need to get past political and societal pushback. The road ahead. Telecom companies are at the forefront of sustainable energy innovation, driving solutions that reduce environmental impact while meeting rising energy demands. The integration of liquid heat displacement systems, renewable energy sources like solar, the efficiency of nuclear power, and the ingenuity of biodegraders exemplify the industry's commitment to a greener future. This can also be a way into a lucrative entrepreneurial enterprise. For example, if you are in real estate business and are able to get past some of the barriers to entry that would allow you to build co-location or data center space, having a reliable and energy efficient location can truly set you apart. I discuss data centers in the Nova, Northern Virginia area more later in the book. As telecommunications continues to connect the world, its leaders are proving that sustainability is not just an add on, it is a fundamental aspect of modern technology infrastructure. By embracing these innovations, the industry is pioneering a cleaner, more efficient energy paradigm that benefits both people and the planet. Chapter 2: As Above, So Below. Terrestrial fiber versus satellite connectivity. In the ever evolving world of telecommunications, the question of fiber internet's future has gained traction. With the rise of satellite internet technologies like Starlink, Viasat, and others, the traditional dominance of fiber optics is being challenged. But is fiber internet truly dying, or is it simply adjusting its role in the broader connectivity ecosystem? To answer this, we'll dive into deployment cost, urban and rural dynamics, and the overall reliability of these technologies. Cost of deployment: fiber versus satellite. Fiber optics is a marvel of modern telecommunications, offering unmatched speeds and reliability. However, its Achilles heel is cost. Deploying fiber infrastructure is expensive, particularly in rural or sparsely populated areas. Trenching fiber lines, acquiring right of way permissions, and installing equipment in low density areas often require millions of dollars per kilometer. In urban areas where population density justifies the expense, fiber deployment becomes more economical. However, as you move to rural regions, the return on investment plummets, making it less attractive for providers to expand fiber networks. Satellite internet, a space age shortcut. Satellite internet sidesteps much of this financial burden. Rather than laying physical lines, providers launch satellites into orbit, covering vast areas with a single infrastructure investment. This makes satellite internet particularly appealing for remote or underserved regions. That said, the initial cost of deploying satellites is astronomical, literally. Launching and maintaining satellites requires billions of dollars, but these costs are spread across a global customer base, making satellite internet scalable and cost effective over time. The verdict: in terms of raw deployment cost, satellite has the edge for rural and remote regions, while fiber remains more economical for urban areas where dense populations justify the infrastructure investment. Urban versus rural. Pros and cons. In cities, fiber has a clear advantage. Its ultra fast speeds, low latency, and ability to handle high data loads make it the go to choice for urban consumers. Fiber connections are less susceptible to interference, making them more reliable for households and businesses that demand consistent high speed internet, like one would expect in a city where there is ample access to professional jobs with remote capability. However, the story changes in rural areas. Here, the cost of deploying fiber often outweighs the benefits, leaving many communities with limited or no access. This digital divide has pushed rural residents to seek alternatives like satellite internet. Rural areas. Satellite steps in. Satellite internet has transformed connectivity in rural and remote regions. With satellites beaming internet directly to user terminals, the need for physical infrastructure is eliminated. This makes it an attractive option for rural communities where traditional fiber is prohibitively expensive. The downside? Satellite internet often comes with higher latency and data caps. It's suitable for general browsing, streaming, and communication, but less ideal for activities like competitive gaming or handling massive data transfers. The verdict: urban areas will continue to favor fiber for its reliability and performance, while rural regions benefit from the accessibility of satellite. Each has its place, depending on the population density and the end user's needs. Reliability: fiber's consistency versus satellite's coverage. Fiber internet, steady but grounded. Fiber internet offers unparalleled reliability under ideal conditions. Once installed, fiber networks are resilient to weather disruptions and provide consistent speeds. However, physical damage to cables, whether from construction work or natural disasters, can lead to prolonged outages in affected areas. Satellite internet, ubiquitous but weather prone. Satellite internet excels in providing coverage where traditional infrastructure cannot reach. However, its reliability can be hindered by environmental factors such as heavy rain, snow, or cloud cover, which can disrupt signals. Latency, while improving with advancements in technology, is still higher compared to fiber, making certain applications less effective. Verdict: fiber wins on reliability in stable environments, while satellite provides a lifeline in areas where fiber infrastructure is non existent or impractical to deploy. Fiber dying? The short answer is no. Fiber isn't dying, it's evolving. While satellite internet is gaining ground, particularly in rural and remote regions, it isn't a wholesale replacement for fiber. Instead, these technologies complement each other. Fiber will likely remain the backbone of urban connectivity and data intensive applications where its speed and reliability are unmatched. Satellite, on the other hand, is carving out a crucial role in bridging the digital divide, providing internet access to regions that fiber cannot economically or logistically reach. As we look into the future, the question isn't whether fiber will die, but how it will adapt to coexist with emerging technologies like satellite internet. Together, these technologies are shaping a more connected, inclusive, and sustainable world of telecommunications. By embracing the strengths of fiber and satellite, the telecommunications industry can ensure that no one is left behind in the digital age, regardless of where they live. Fiber isn't going anywhere. It's simply finding its place alongside satellite in the ever expanding web of global connectivity. Chapter 3: we have chemistry, erbium, the periodic table, and telecommunications. In our day to day work in telecommunications engineering, it's easy to separate our tasks from the sciences that make them possible. We've grown so accustomed to the groundbreaking discoveries that underpin our field that we might forget how extraordinary they truly are. This book delves into physics and particles like photons and neutrinos, as well as social sciences, addressing the digital divide and global conflicts. For now, let's focus on a different scientific realm: chemistry. Surprised? If so, you may fall into the category of those who have become engrossed in the task of configuring via GUIs or CLIs, forgetting the scientific marvels that power telecommunications. This chapter aims to rekindle your sense of wonder by spotlighting a fascinating element from the periodic table: erbium, a rare earth metal that plays a vital role in modern telecommunications. The discovery of erbium. Erbium was first identified in 1843 by Carl Gustav Mosander, Swedish chemist who discovered it within a mineral gadolinite. Mosander's work was part of a broader effort to isolate rare earth elements, many of which were initially grouped together due to their similar chemical properties. Despite its discovery in the 19th century, erbium's practical uses remain largely unexplored for over a century. It was later found that this element had unique optical properties, particularly its ability to emit light in the infrared spectrum, which eventually brought it into the spotlight. These properties laid the foundation for erbium's pivotal role in telecommunications. Erbium's first uses in telecommunications. Practical applications of erbium in telecommunications began to emerge in the late 20th century, thanks to advancements in fiber optics. The invention of erbium doped fiber amplifiers, EDFAs, in the 1980s revolutionized long distance communication. Before EDFAs, signals transmitted through fiber optics would attenuate over long distances, requiring frequent electronic regeneration. This process was not only costly, but it also limited the scalability of optical networks. If you've ever implemented or troubleshot layer 1 or layer 2 services over a certain distance, you are familiar with the popular 1550 nanometer wavelength that you can hand off from an optical chassis or router. This wavelength comes from using EDFA's ability to pump a lesser wavelength up to 1550 nanometer and expand the distance of a signal with less degradation. How fiber optic EDFAs revolutionize communications. EDFAs transformed fiber optic networks by allowing signals to be amplified directly in the optical domain without the need for electronic conversion. When an optical signal passes through an erbium doped fiber, a pump laser excites the erbium ions, amplifying the signal without distorting it. This innovation drastically reduced the cost and complexity of a long distance data transmission, enabling the development of high capacity networks that form the backbone of our internet, telecommunications, and global communication systems today. Standard optics can get 80 to 100 kilometer distance, about 65 miles, and in a lot of cases, an EDFA added at the end of that, you can amplify the signal of wavelengths between 1535 nanometer and 1565 nanometer to keep it going for another 70 to 90 kilometers with minimal signal degradation. This extension can make a big difference. For reference, this is approximately the distance between Washington, D.C. and Baltimore. The future of fiber amplification and EDFAs. As the demand for higher bandwidth and faster speed grows, EDFAs continue to evolve. Researchers are exploring ways to enhance the efficiency of erbium doped fibers and integrate them into the next generation optical systems. For example, hybrid amplification technologies, combining erbium doped fibers with other amplifying materials to extend amplification ranges and improve efficiency. Space based applications. EDFAs are being tested in space based telecommunication systems where their ability to operate over vast distances is particularly valuable. Specifically, erbium is being used for laser communication outside of the atmosphere to communicate over the expansive distances of space. Quantum communications. As quantum technologies advance, erbium could play a role in enabling secure quantum communication by amplifying weak quantum signals. Rekindling the love for science and telecommunications. The story of erbium is a reminder of deep interconnection between the sciences and engineering. Chemistry, like physics and social sciences, plays a crucial role in enabling the technologies we rely on every day. By appreciating the scientific breakthroughs that power our field, we can reignite our passion for innovation and problem solving. Telecommunications engineering isn't just about GUIs and CLIs. It's about the incredible science that allows us to connect the world. Let's never lose sight of how cool our careers truly are. So, the next time you configure a network or troubleshoot a fiber connection, take a moment to learn more and marvel at the chemistry and the science as a whole that makes it possible.